Hello, and welcome to another episode of nanoCHATs. And this is where members of the Ionic Viper community get together and do a critically reflective teaching practice, which is to share our experiences in the classroom with each other. So I'm Shirley Lynn from the Naval Academy, and today I'm joined by three of our Viper Fellows, and I'll let them go ahead and introduce themselves now.
Hi, I'm Megan Lazorski. I'm an assistant professor at Metropolitan State University of Denver in Denver, Colorado. Currently, I teach General Chemistry 1, but I also teach Inorganic Chemistry and Advanced Inorganic Chemistry.
I'm James Dunne. I'm an assistant professor at Central College in the very lovely town of Pella, Iowa. I teach inorganic chemistry at both a sophomore and senior level, and then along with some environmental chem and occasionally organic chemistry.
Hello, I'm Rudy Luck, and I'm at Michigan Tech University, and I teach inorganic chemistry and general chemistry during the summer months.
Today, our nanoCHAT topic is how do you level the playing field for students coming into your classroom with different levels of background or preparation?
Yeah, that's I think one that's near and dear to all our hearts. In my case, the inorganic class I teach most, it's designed to be taken by first years in their second semester, but that's only about half to 2/3 of the class. So I get people who are any range from sophomore to senior as well. And I don't know what their background is or their preparation. And so I only really find out after the first exam. And what I use then is a set of exam corrections, which is, it's not unique to me. I find it's misnamed. I don't actually alter the exam score. It's a separate own assignment, kind of like a souped up homework assignment. But it's meant to self-differentiate that, you get the exam grade back, whatever you got, you have until the next lecture, open book, open note, fix the things that you missed on the first one. If a student gets a 95, they've got 5 points they've got to make up, and it shouldn't take them long. They're near where I want them to be. If a student gets a 55, it's going to take a little bit longer, and it should. They need a little more reinforcement. We need to build that knowledge because we're going to need it later. And so it's a nice way to try and make sure I don't lose the bottom half of the class while still making sure the upper half is engaged. And then when I add to it, I usually set up a meeting with the bottom 20% and ask them to come talk to me, bring your corrections, let's go through them together. Let's make sure that you have a rigorous understanding here. You're the ones I'm most worried about, so let's take a little extra time.
Oh, Rudy, I think you had a question?
Yes, James, I was just curious. Now, you mentioned that the first semester of the chemistry degree at your school, the students would be enrolled in university chemistry, and finish university chemistry in one semester, and then they would jump into your course. So, like, the two questions I have is how many chapters? A general chemistry book normally has 25 chapters. How many of those chapters are completed in the first semester, or the first term of enrollment at your college? And secondly, how many students do you have enrolled in the inorganic course that you teach?
Yeah, so my enrollment runs, I answer the second question first. The enrollment's between about 20 to 36, depending on the year. So it's a smaller school, it's a smaller class, which means those individual meetings that I do, I can do that. I can make the time more readily there. In terms of the Gen Chem content, we do have a one semester Gen Chem class. They cover what I would estimate to be around 3/4 of the chapters in there. I mean, they're never going to cover the coordination chem. That's left to me always. But the three topics I think that show up more frequently in Gen Chem that they don't see would be maybe 4 topics, I guess. Solid state chemistry, electrochemistry, molecular orbital theory, and then nuclear chemistry, which doesn't seem to fit anywhere, but I take it. But of those, I mean, solid state and MO theory are very heavily inorganic anyways. I'm comfortable walking them through all of that. Electrochem, there's a lot of overlap, and I can do that well.
Well, thank you, James. We were just joined by another Viper Fellow in our group, and we're going to pause here and let the new person introduce himself.
Yeah, hi, this is Claude Mertzenich, Chemistry Department, Luther College. I'm sorry I'm running late. I had kind of a situation here with a health issue with a student, and then I realized, oh my gosh, I've got to go to this meeting. So anyway, I was able to break away from that and get to this. So it's very, very good to see all of you again, some of you again. So I teach at Luther College, and the courses that I teach are introductory chemistry and inorganic and solid state. So we have a traditional upper level bridge between undergraduate and graduate level inorganic course that is a 1-semester course, and that encompasses physical inorganic chemistry as well as organometallic, a little bit of solid state. And then we have a full half-semester course on solid state chemistry, which I taught last semester. So we have a lot of MO going on in our upper level full semester inorganic chemistry, that's Chem 372. And in the solid state, we use a book specific for that. That's Smart and Moore's book is what I've used for a couple of times, and it's worked reasonably well. So maybe I'll give you a little feel for the numbers in the classes, and maybe that's helpful. And then if you have some other comments or questions that maybe I'm not addressing and others have, you can just let me know. But I have currently 9 students in this 300/400 level course. It's called Chem 372. In the past, it's been a 400 level course, but and in solid state, I had, I think, about 6 students. So relatively small classes, very amenable to, plenty of interaction with the students. We cover the range of topics that seem to be useful, for example, for helping the students to prepare for a graduate entrance exam, or getting the coordinate. I heard James mentioning coordination chemistry, getting the coordination chemistry that they really don't get anywhere else in the curriculum. So in our curriculum, in the introductory chemistry class, the 100 level classes, there's really no mention of coordination chemistry. So the only place they're getting that is in our upper level course. Now, it's unfortunate some of our students will graduate without having taken the upper level inorganic course. So I think that's a real deficit, but it's sort of the nature of the way the system works with the numbers of students we have, the number of majors, and how the curriculum's arranged. I do everything I can to advise my faculty colleagues to get our chemistry majors into inorganic, so they see coordination chemistry, they see organometallic chemistry, they see some bio-inorganic chemistry. And last thing I think for the moment that I can think of is I'm using Housecroft's text in that upper level course, which I've found to be a very good text, and covers a range of topics that we need to prepare our students for graduate programs and beyond. So hopefully that's a helpful introduction.
Definitely. I'm just going to remind everyone of our question, our topic for today, and what we're talking about is how we each level the playing field for our students of different background and preparation. And Rudy's going to go ahead and share next. Go ahead, Rudy.
Yes, thank you, Shirley. The very interesting topic, but it has to be viewed from the perspective of the student clientele that we have here at Michigan Tech. It turns out that since we get on average 250 inches of snow, we are one of the whitest schools in the nation, with a population at the undergraduate level that's 90% white, maybe 1% black, 2% Hispanic, and the rest various mixtures. So when I look at a class, there isn't much what we would classify as diversity that I'm looking at when I teach. It is, there are more females than males, but they're all white. So therefore, in terms of bringing people up to date, some of the more relevant aspects of diversity do not really enter into the equation here. What really surfaces is the work ethic and the ability to perform. So I provide a background lecture, which deals with information they should have gleaned from physical chemistry, organic, and general chemistry, namely chemical bonding, group valencies, molecular shapes, hybrid orbitals, how to name compounds, atomic structure, and periodicity, properties of the periodic table. And that information, I believe, it doesn't necessarily level the playing field, because it is fundamentally impossible to level the playing field, because different people have different abilities. So that would be how I would proceed essentially making sure people have equal access to the information that is required to conquer this course. One thing I have discovered is that it is very useful to get the ACS exams, because different curricula around the country is useful in preparing students. But unless one actually looks at the ACS exams and examines the material there, I'm not necessarily teaching to the content of that exam, but I would hope that the ACS committee that recognizes different degrees would expect people to teach courses that would allow students to do reasonably well in these subjects. So for instance, even the general chemistry exam, which I will be administering to some students I'm doing in recitations, has 70 questions which they require people to answer in 110 minutes, which I find to be very difficult to do. So I will be administering that exam. And I think if you look at the inorganic chemistry exams, there are 2 of them. You cannot do those 2 exams with just 1 semester of inorganic chemistry. So it is a very difficult career, as Claude had mentioned. The 2nd semester really is crucial. Thank you.
Thanks, Rudy. I had a quick question. How would you say the students react to this primer, this 1 week, preparation? Is there a difference in their attitude and approach to that time?
Yes, that's a great question. I do know from, because I used to run the University Senate here, and I was part of a committee, or me and the provost had decided that we should have evaluations in the 4th week of a semester, because it makes no sense to have evaluations at the end of a course. If you have the evaluations at the end, there's nothing to implement there. The students are already gone. And then the memory of the final exam weighing in their minds may taint the nature of the evaluation process. So after 4 weeks, we have an evaluation. And some of the comments there are that perhaps this has taken up too much time from students who might be more or less challenged on it. So what I tend to do to make up for this kind of thing is I intersperse this material with a bunch of clicker questions. So if I speak to an introductory topic, I would expect to see 90% correct on the thing. And I turn out that I would get like 60%. And then I could see a progression as the lectures progress from 1 day, like it takes 3 weeks, 3-day lectures to go through this material. I see an upward progression. So this means that they're clearly reviewing the material and advancing. So I think that's one way to get over it. The big problem I have now is that it has taken a long time. And I also use the Cambridge database, which is an amazing compilation of structural information. And I had a big complaint the last time because they were really resentful of the time it took to learn how to use the Cambridge database, which to me is just a matter of moving the mouse around or like surfing the web. And it should be a trivial process to master the Cambridge database. The Cambridge database 20 years ago is completely different from the Cambridge database today. So which those of you who know about the Cambridge database can reflect upon that you needed to almost know programming to use the Cambridge database. But now it's incredible, So I may reduce this material and spend some more time on the Cambridge database.
Thanks. Megan, would you like to go next?
Yeah, sure. Thank you, Rudy. Actually, you gave me a good segue because I prepared a topic from my general chemistry class, because that's where I see a lot of the variety of preparation in our students. MSU is a public access urban institution, MSU Denver, and so we have a wonderful variety and actually wonderful diversity of students here. We're a Hispanic serving institution, and we are approximately 48% students of color. And we are, I think, 50% first generation. And we have a ton of amazing programs for like DACA students, as well as migrant student programs and things like that to try to support our population. And so that's something I feel really strongly about as part of our university mission, as part of my mission personally as a human being. And so one of the things that I really tried to do to try to level this playing field is to help students tackle the problem solving skills. Especially, I think this is important on the general chemistry level because not all general chemistry students are chemistry majors, but a lot of them have technical majors. And I think one of the biggest issues that students have when they struggle with science is with problem solving, how to take these disparate pieces of information and bring them together so that you can really like tackle the problem or look at it from a different angle and then figure out how you can solve it from there. So I feel like once students start to be able to grasp these concepts, that's when they really start to improve as students and as academicians. So I hold these problem solving sessions for my general chemistry students. I hold one every week, and then I hold 2 every other week. So like there's a makeup session every other week. And I rotate the session throughout the week so that students that, you know, are on campus, we're also a commuter campus. So students that are on campus or have work or something or other duties on different days will be able to still come to a certain proportion of the sessions. And the sessions are really guided by inquiry-based working in small groups, and there are no stakes. The students, it's not mandatory, and it will not work against their grade in any way, but they are outside of class and they're small group, and I try to stay really hands-off so that the students are forced to come up with these problem-solving strategies on their own, but also in concert with their peers so that they can use their peers as good resources to try to generate these different problem-solving ideas and approaches. And so I feel like some students really, this resonates well with them, some students it doesn't, but I've tried really hard to kind of look at how this program is structured and then try to implement it in a way that's really accessible for all students. No matter, you know, if they're a mom of 2 or if they're, you know, working nights or whatever, so that each student can benefit from this problem solving ability. I also, this last thing I'll say, I also feel like a great responsibility to try to help these students, especially at the Gen Chem level, because I've seen a bit of data, institutional data that shows a strong correlation between students, their performance in general chemistry and their graduation rate, like overall. And so I feel like this is a really critical time to try to build these skills.
So Megan, for the small groups, you've got a revolving number of students each week, depending on schedules. Do you assign the groups? Do you let the students pick them? Do you mix it up?
I assign the groups because a lot of times, like I said, I'll do one set every week, but then on every other week, I do a makeup session. So on the makeup session, it'll be like they can make up, you know, problem solving set 1 and 2 or 2 and 3. And so often I'll be like, you guys can work on whichever set, but then after we get through the makeup session, then they can't work on it anymore. It's like that one's done, and I'll post the answer key so that they can like look through and, you know, use them for exam study and stuff like that. So when I assign the groups, it'll often just be like 2 to 3 students. I try to keep it 2 to 3 students. I don't like them to get much larger than that. And then I'll, you know, mix them up. I don't try to like keep them together with particular people, but then also it's dependent on which problem solving set they're on.
Thanks, Megan. Claude, would you like to go ahead?
I'll be very brief since I've been asked to be brief in terms of leveling the playing field. I'll just put a link into the chat about the curriculum that we went over to in our introductory chemistry course. And it's the CLUE curriculum. Long story short, it truly is an atoms first curriculum. And by that, actually, it's a nucleus first curriculum. So we start out with positive charges is where we go and build everything up through positive negative interactions. Long story, very long story short, we implemented this curriculum starting last year and we're still doing it. Okay. Then in the upper level inorganic course, I start with chapter 3. In Housecroft, not chapter 1. Chapter 3 is Introduction to Molecular Symmetry. None of the students, the upper level inorganic, the upper level chemistry students have had a symmetry approach. And so they're on the same playing field. That's what I've got.
All right, I have a question. So in your CLUE course, we also teach an atoms first, and in my inorganic course, I actually try to teach a nucleus first type of approach. So when you say nucleus first, what do you mean by that? Like, are you kind of starting with a standard model, or are you kind of just starting with like, you know, Coulomb's law? How do you go about that?
a proton. We start with a proton, literally, and then we look at the potential energy associated with a proton interacting with another proton. Then we look at the potential energy of a proton interacting with a negative particle, call it an electron, if you will, and you develop the potential energy curve for plus minus interactions and show that there's a potential energy minimum when you have plus minus interactions for atomic systems when the atoms are a certain distance from one another. Then once you do that, then you can build up molecules and you start to look at plus minus interactions there. Everything is plus minus all the way across. Even right now, we did stoichiometry. We do stoichiometry in the second semester because we don't build up those molecules until we get to that point. So when I say nucleus first, that was a little vague, but I really mean we start with a point charge and ask ourselves, how do plus plus interact? Well, they repel. You know, how do minus minus interact? Well, they repel. How does plus minus? Well, they attract. Okay, and then we put that in light of a gravitational model, which is analogous to a plus minus interaction. I don't know if that helps you.
Yeah, it does. Thank you.
Well, I just want to thank all of our participants today for this wonderful chat, and just reminding the audience joining us on YouTube that you can actually go to our Discord channel and ask our wonderful fellows questions and make comments about what they talked about. And you can access that through ionicviper.org. And we'll be back with more nanoChats in the future. Thanks, everyone.
Thank you.
Thank you.
Thank you, Shirley.